Let's talk about manual transmissions. Of course, these are both been cut away, but for many years, the Synchromesh design is what has been in use. I mean, we're talking for many, many years, meaning these gears are always in mesh. So when someone is grinding the gears, so to say, it's not the actual speed gear or the gear on the counter shaft that's grinding. It's this segment in here. You want to bring that a little closer. When we select a gear, I'm going to select second gear, for example. What grinds is the little dog teeth. These teeth right here, which is attached to this gear. I'll show you more particular here. Here's the same kind of a speed gear. And here's the dog teeth, and of course here's the speed gear itself. And here would be the synchronizer ring. When the sleeve comes over to select the gear, or the slider as some would call it, it pushes this synchronizer blocking ring, synchronizer ring, up the ramp. This is a cone-shaped piece. It'll push it up the ramp, which slows the gear down in order for the gear to be selected. It all happens pretty quickly, obviously, but that's the process. There's actually some little lines for gripping, these little grooves, I should call them, for gripping and trying to hang on to this cone-shaped shiny area to, again, kind of cause some braking action that will slow the gear down so it can be selected smoothly. But again, these can wear down when someone's grinding. You're not pushing the clutch in far enough, or there's a synchronizer wear issue. Let's continue. I want to disassemble and talk about the 4 primary shafts. Some would call 3 primary shafts. I'll add a 4th one, the reverse idler, but let's go ahead. This is very convenient. I'm going to remove, first of all, the clutch shaft, or the input shaft. It's called either name, clutch or input. Obviously, this is the clutch part that would go inside the manual clutch. Of course, the driver engages and disengages the clutch. Input shaft, of course, this is the input from the clutch. Okay, we'll get to that later. This whole thing would be the main shaft. Of course, this is all assembled with gears and synchronizer assemblies. Here is a main shaft without all the gears. The speed gears actually slide on to this shaft and, of course, can rotate freely. The reason we have these segments here, or these splines, is for the synchronizer hub. Here's a synchronizer hub. It's not the one that fits this shaft, but the synchronizer hub is what goes onto these splined areas, and this sleeve or slider that selects the gear. Thus, this is what locks a speed gear to the main shaft. All of these gears can turn independent and freely. Okay, whoops, here we go. Independent and freely. But when they're in mesh with a third shaft, this third shaft we'll call the counter shaft assembly. This is one hunk of metal, in essence. All of these gears have been machined to this piece of metal, this shaft. If this ever chips or breaks, it's an expensive repair. Replacing a speed gear because of a broken or chip problem is not such a bad deal. Now, sometimes the speed gears or teeth themselves are just fine. Again, what the problem often is these dog teeth get rounded off, really dull. They actually come to mostly a point. And that helps the sleeve that would engage the slider or the sleeve engage smoothly as well. Okay, and of course, here's a really simple shaft number 4, the reverse idler. Let's put this back together. To do so, I'm going to input or clutch shaft, main shaft, counter or cluster, as some would call it, and of course reverse idler shaft. Those will be the 4 shafts that make up a typical manual transmission. Let's put this back into this case. There we go. Okay. Now as far as power flow and operation, I'm going to switch over to this transmission. Set this aside, and we'll come over here. Let's identify the components one more time. Clutch or input, from about this point on, is the main shaft. Of course, the main shaft is what the driveline will hook onto. These gears are all, again, in constant mesh with the lower or counter shaft, cluster shaft. Those are the 2 names it's known by. Overdrive is back here, the 5th gear overdrive. Let's go ahead and we'll just do some power flows here. I'm going to use a white mark here and a white mark here to talk about ratios while we talk about power flow. For example, I'm going to go ahead and select 1st gear. 1st gear we know is selected when the synchronizer is covered up by this sleeve or slider. It engages the dog teeth of this gear to the main shaft so that this has to transmit power. For example, I will go ahead and of course 1st gear is always the largest gear, 2nd gear, 3rd gear. We can call it 4th gear, the clutch input shaft, clutch gear. That'll be direct drive. But we'll get to that point. So 1st gear, power flow comes in. Okay. These 2 teeth are always in mesh. Since this gear is locked to the main shaft and the power flow comes over to this part, this gear in the counter shaft, back up to the main shaft with 1st gear locked to it and on out. For example, let's count the ratios. This is turned once. This is turned, well, definitely not a full turn, maybe a quarter turn. 2. 3 revolutions, almost there. So we'll just call it 3 1/4, maybe it's 3.2 or something of that nature, that kind of a ratio. Let's shift to 2nd gear. I'll line my white marks back up, neutral. 2nd gear, you see that one selected? Power flow comes in to this gear, down to the counter shaft. Because this gear is now locked to the main shaft, this is our 2nd gear on the counter shaft, and here's our 2nd speed gear on the output shaft, main shaft. Let's do the ratios again. Input shaft has turned 1 revolution. This is turned probably a little better than a 1/3 of a rotation. 2 revolutions, almost there. So 2 and a little bit more, 2.1, 2.2 turns, something of that nature. Okay? Let's go to 3rd gear. Whoops. 3rd gear. Let me get my white lines marked up a little better, lined up. 3rd gear. Power comes in, down, over to this gear, 3rd gear on the counter shaft, 3rd gear on the main shaft. Ratios. 1 revolution, and maybe 1 and a little better than a half, or not quite 1 1/2, sorry, not quite 1 1/2, 1.35 or something of that nature. Okay. 4th gear. 4th gear is kind of neat, because all we're doing is locking input shaft to main shaft. the cluster is bypassed, not even has purpose in fourth gear. To prove the point, let's do the ratio. Fourth gear, this is 1:1. Do that again. 1:1 ratio. They're directly locked together. Again, the counter shaft has no purpose. Let's go to overdrive. Overdrive is back here. Sliders engaged. Power flow comes to here as usual, down to the counter or cluster gear, clear over to fifth gear. Notice how big overdrive is, and how small fifth gear overdrive is on this one. And this is just what I called it. It's going to be an overdrive situation, meaning I get more out than I'm putting in. Everything we've done thus far has been what we would call underdrive. Whereas overdrive, we're going to get more speed out than what we put in. Here we go. Let's do the ratio. I'll rotate this, and this has already gone 1 revolution, and this hasn't gone quite 1 revolution. So we'll call it 0.8 something, maybe almost 0.9, 0.85 or something of that ratio. So there's what we would call the power flow. What we just did is power flow of a manual transmission. We named the shafts. What I want to do now, the next thing to talk about is the synchronizer assembly. And of course, this one here is all assembled. We'll get to that in a minute. Okay. You have to be careful because the synchronizer teeth or the little keys sometimes can pop out. And that's a challenge to get them back in at times. But anyway, again, the synchronizer hubs, okay, this middle piece I'm moving, that's what splines to those places on the main shaft. These are the heart and soul of locking a gear to the main shaft. A speed gear, that is. Okay, so I'm going to set aside these shafts. Cluster shaft, right? And here's a speed gear. There we go. Speed gear freely flows or rotates on this shaft here. In order to engage it, of course, the slider moves over and locks the gear to the shaft. Therefore, power transfer can occur. Synchronizer ring, some would call it a blocker ring. Synchronizer sleeve, that's the big piece I'm sliding back and forth here. This is also a synchronizer sleeve. I'm moving out here. And with a synchronizer hub. Hub, again, is splined to a shaft, a main shaft. The synchronizer hub and sleeve are what engage the speed gear to the shaft. It's not really a complicated principle, but it is the heart and soul of how a Synchromesh manual transmission works. These keys are what help keep the gear engaged. There are actually 2 things that keep a gear selected, that keep this sleeve in place. These keys are part of it. Another part of it here's another cutaway transmission unit. The other aspect that helps keep a sleeve engaged is what we call the detent. Now, before I take the detent and spring out, I want to show you how this works. This shaft right here is going to slide in a moment. See that shaft slide? Now there's a groove. That's okay. There's a groove or a detent, and this little steel ball and spring is what's going to hold or lock the gear into place. Essentially holds the sleeve in place. Show you how simple this is. Sometimes when disassembling a transmission, it'll say remove the detent assembly. And this is all they're meaning. I'm going to push this spring up a little more. And there is the little cage and its spring. And this is a steel ball. And again, that steel ball is what bounces over and keeps the ball bounces over and stays in the grooves based upon some spring pressure. Okay. Detent assembly. Let's talk about a manual transaxle. Now, I've already got the case part way off, as you can see in this video. But I want to at least give you an idea of where we're at as far as orientation. For example, here's the input shaft. And of course, the manual clutch connects to here. Here's where the CV shafts, of course, this is a chopped off one. But here's where the CV shafts come out and drive the wheels. There's a CV shaft for both sides of the vehicle. I think you get the idea. These axle shaft seals are sometimes replaced because they leak gear oil. What I want to do next is go ahead and remove the case cover. I know I've made it look too simple. They don't come off quite that easy. But nonetheless, let's go ahead and identify the shafts and everything inside here. Typically, manual transaxles have two main shafts, as you can see. The one that goes clear through to the clutch, okay, we're going to call it the input shaft. That's what it's called. So this is the input shaft, and here's the output shaft. The reason it's called the output shaft is down inside here. That has one more smaller gear. We'll pull this assembly out in a minute. That small gear meshes with the big ring gear, and that is our output. And of course, our CV axles come out of here. Now, what I don't have installed right now, of course, is the slider, the fork assembly. And to make the video easier, I decided to not have them installed. I'll move them manually. But this is the part right here that a shifter is moving a different fork at a time. And it selects one. Okay, I've got a few things missing here, but this is what we call the interlock assembly of my shift fork and rails. These are the rails, of course, the shift forks. Okay. Let's do a little bit of power flow of a manual transaxle before I actually pull these shafts. For power flow, I'm going to have to turn the clutch or input shaft right here. Okay. Can you see these marks on the teeth? That's what I want to focus on for a minute. Now the principles are just the same as a manual transmission. We have synchronizers, blocking ring. We have a sleeve, slider. Underneath here are there's three keys, usually always three, synchro keys, and of course the hub. That's the hub. Here's the sleeve, Okay. This is going to be first gear, second gear, third gear, fourth gear, and fifth overdrive. We also have the differential and final drive assembly, and we're going to get to that. That's going to be the focus of this segment. But the input shaft and the output shaft both have speed type gears and counter shaft type gears. Let me explain. I'm going to spin with a pair of vice grips under here this input shaft. I'm going to rotate it. You can see how this gear is spinning at a different speed than this gear. This gear is a counter shaft type gear, whereas this gear is a main shaft type gear. Okay? Both shafts have synchronizer assemblies. Both shafts have counter shaft type gears. These are down here on this input shaft. This here is the number one or first gear for this input shaft. Let's talk about gear ratios now. What I mean by that is we're going to talk about the speed gears and the ratios that occur here. We're also going to point out the final drive. Down inside here is the final drive gear, and it rotates the big ring gear. And then we'll refer to what's known as overall ratio. So to review, on the input shaft and the output shaft, I've got some gears, and I've actually counted out the teeth. And if we divide these numbers, and the real formula is this formula right here in the red, driven over drive, driven gear over drive gear. That's how you calculate your ratios. So we're going to have our speed gear ratio in this column. And again, that's a calculation of these two gears that are in mesh with each other. We'll have an final drive ratio, and of course it'll be constant. And the final drive ratio is 4.06 to 1. And again, we're going to show that, leaving us an overall ratio of, say, in first gear, 12 teeth, 39 gives me a first gear ratio of 3.25 to 1. Times that by the final drive, 4.06, gives me a overall ratio of 13.2 to 1. So what does this all mean? Now, we've already discussed some things about gear ratios here. But I want to clarify, and that is, first of all, I'm going to do a power flow experience as well as a ratio experience. We have our speed gears, okay? In fact, this is a speed gear, that's a speed gear. That's actually a counter shaft type gear, we mentioned that earlier. Then up here, we've got, this is a speed gear, this is a speed gear. We know what speed gears are when there's a synchronizer sleeve to engage them. Let's talk about first gear ratio, final drive ratio, we've touched on that, but the overall ratio is what I want to demonstrate as well. So here, let's go speed gear ratio. We already pointed out this is the input shaft, this is the output shaft, this gear down here to this gear, this is our final drive ratio. It never changes. Okay, this is the gear that has 12 teeth, this is the gear with 39 teeth. The formula is, as we pointed out on the chart, driven over drive. 39 teeth divided by 12 teeth gives me a speed gear ratio of 3.25 to 1. I've already painted the gears. Let's do it. So, 1 revolution, 2 revolution, 3, and I'm going to rotate about 25% or 0.25 more to get this back to where we started from, the output, first gear. Now, having done that, let's also focus on the final drive to calculate our overall ratio. Remember from the chart, there we go, we're back to where we started from. Speed gear ratio times final drive ratio gives me an overall ratio, in this case, of 13.2 to 1. I'd better make sure I'm in first gear. Okay, it worked. We're selected first gear. I'm going to paint this tooth right here to show you exactly what I'm trying to explain here. This input gear is going to have to turn 13.2 times to the ring gear's final, or 1 revolution. I take my speed gear calculation times final drive ratio, and I come up with an overall ratio. Let's demonstrate. There's 1. Hasn't moved very far. There's 2 revolutions. 3, 4, 5, 6. If you'll notice, the painted tooth is over here not quite 180 degrees away. 7, 8, 9, 10, 11, 12, 13. We're not quite there. And we're going just a little bit more of a revolution here. And that's now back to where it started from. 1 revolution, this turns 13.2 times. The input gear of the whole process turned the final output gear 13.2 times to 1, the overall ratio. Let's shift gears. Let's do this again in second gear. Okay. We're going to do the speed gear ratio and then the final drive ratio. All right. I might even paint these gears. So I went up from first. I'm up here to second now. This synchronizer is now in second gear, obviously. I'm going to paint. Let's go with this tooth here and that there. I think that'll be a good enough mark. I'll worry about this mark later. For now, here we go. Based upon the chart we looked at earlier, this gear has 21 teeth. This gear has 37 teeth. Driven over drive makes it a 1.76 to 1 gear ratio. Okay, so the input gear has turned once, right? And now the output gear is turned once, and this is not quite made 2 revolutions. It's gone 1 3/4, 1.76 revolutions. But what about, let me back it up here. What about the overall ratio and the final drive? Well, if I take this ratio here, second gear, ended up being 1.76 to 1, times my final drive of 4.06 to 1. I take 4.06 to 1 times my 1.76, gives me a final overall ratio of 7.15. This will turn 7 times, a little more than 7, to my speed gears ratio. Let's demonstrate. Power comes in to this gear, transfers over to this gear, on down to the final drive, out to this ring gear, again to turn my axle shafts that come out of this hole here, my CV shafts. Alrighty, I already got my mark there, got my marks here. I've got to watch this turn 7.15. There's 1, right? There's 2 revolutions. 3, 4, 5, 6, 7. It happens to line up here, but that's not my point. We're almost lined up. Let's just go a little bit beyond 7, and that makes 7.15. Input gear to my final output overall ratio of 7.15. I think we've said that enough. Go to third gear. Third gear. That's fourth. There we go. All righty. Let's paint some gears again. Maybe I'll wipe these off so it's not confusing. Get all these marks off best we can. Third gear. Let's just choose this one. And let's choose this one. Show our ratios. I think that'll be plain enough. In this instance, this gear has 29 teeth. This gear has 34 teeth. A ratio of 1.17 to 1 ratio. Still, my final drive is 4.06 to 1. We've explained that. Power's going to come in. Come up to this gear, over to this gear, the output shaft, down to the final drive gear, turns the ring gear. Here we go. Let's do it. In fact, I'll be marking that later. Let's go ahead and get the speed gear ratio. 1.17, it's almost a 1-to-1 ratio. 1, and it's almost there. Okay, I had to turn that once. This had to turn 1.7 revolutions to turn the output once. Let's do this. Let's count this gear's input revolutions to the, again, the final overdrive. The overall gear ratio. Make sure we got this marked good. If I take 1.17 ratio by the final drive ratio, it gives me a final of 4.73 to 1. So let's go 4 3/4 of a turn. 1, 2, 3, 4. Here's my mark coming around. And that just lined up. This is over here. 4.73 revolutions. Okay. Fourth gear actually calculates out to be a bit of an overdrive situation. But when you calculate the overall ratio, it's designed to do what's right for the car and its application. What's going to give us the best torque, best economy, best emissions to propel this vehicle effectively down the road. Okay, so I've already slid into fourth gear. Oh, it'll stay, I'm going to have to hold it. I'm going to paint a tooth. I'm going to paint this tooth. Here we go. 33 teeth. 30 teeth. The input is larger than the output. Driven over drive gives me a calculation or a ratio of 0.9 to 1. This is going to turn 1 revolution before this one does. That's overdrive. It's already made it. This one's not there. 0.9 to 1 ratio. Now, let's do the overall ratio. The final drive times my speed gear ratio. Here's my gear, paint. And here we go. The overall 0.9 to 1 ratio times my final of 4.06 will give me 3.7. We're really picking up speed. Here we go. Here we go. 1, 2, 3 point. We're not 4 revolutions, we've got 3.7 revolutions to turn the final drive, the final ring gear, the overall ratio, 3.7 to 1. No more fourth, let's go to fifth now. Fifth gear. Power comes in the input shaft, transfers from this speed gear over to the output shaft, down to the final drive, out of the ring gear, obviously. Here we go. This gear has 37 teeth. This gear has 26 teeth. Driven over drive gives me a ratio of 0.7 to 1 ratio. 0.7 times 4.06 gives me a final overall ratio of 2.4 to 1 ratio. 2.84. Let's do it. I'm going to paint this gear. I'm going to paint this gear. Here we go. Let's start. This is only going to turn or rotate 0.71 to make this one spin once. If I get more out than what I put in, obviously that's an overdrive situation. It's just rotated once. This is over here at 0.7 revolution. Now, let's do the final drive overall ratio. Again, I'll paint a new gear. This is starting where it is. And we're looking for about a little less than 3 revolutions, 2.84. 1, And this has already moved a third, roughly. 2 revolutions. 3, went too far. There is my 1 revolution. There is my 2.84 revolution mark. That's 5th gear. Power flow, ratio, final drive ratio, overall ratio of 2.84. Let's throw in reverse while we're at it. Reverse gear. Reverse is different because it's going to make this turn the opposite direction, obviously. I'm actually going to just get rid of that sleeve for now. Reverse, I have to introduce or engage the reverse idler gear. Here's the reverse idler and reverse shaft. I'll put it back in. Okay? Your shifter linkage would actually move this up into place. Before I do that, notice that reverse is spur type gear teeth. It's not always the case, but it's quite often. They're noisier. That's why you hear that little growl or that whine, that gear whine in reverse. Reverse gear ratios are often similar or close to first gear type ratios. So my driven over drive formula shows 41 divided by 13 gives me a 3.15 to 1 ratio. And my overall at 12.8. Let's do it. So, I'm going to engage reverse, and I'm going to paint a dot here and here on those. But yet these 2 gears never actually touch each other. They're joined by the reverse idler, so I can get a 3rd gear in the process to make an opposite rotation. Okay, here we go. If I can count my ratios here. I'm looking for about three revolutions. 1, 2, 3, and a little more. There it is, 3.15. As far as the overall ratio, I'm going to back it up to a gear I've already painted. Well, maybe I will change it, just so I can keep this in the same location I always have. I keep turning the same direction, so about 12.8 to 1, but this is going to turn opposite. What it has all the other ratios. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I gotta go 12.8. And I'm already at the 1 revolution, not quite the 13. 12.8 to 1 ratio. That is the gear ratios of a manual transaxle. Once again, we have an input shaft and an output shaft. We have a final drive. We already demonstrated earlier, first gear, how the power comes in from the engine. Crankshaft basically is turning 13.2 times to 1 to the final drives, 1. And the power flow goes straight to here, down to the final drive gear and over to the ring. Second gear, power comes up to this gear, over to this gear, and down to the final drive. Third gear, power comes into this 3rd gear here, to the output shaft, down to the final drive. 4th gear, you get the idea. I'm up to this gear, down to the final drive, out. We removed the synchro from overdrive, or 5th gear, sorry. 5th gear, power comes in, over to this gear, and down. So what does this look like in here? Okay, so here's the input shaft and the output shaft. Here's what they look like side by side, laying down. This also allows us to look at this final drive gear. This is the gear that's always in mesh with the big ring gear. That's the 17-tooth gear that meshes with the big 69-tooth ring gear. Final drive. The rest of these are speed gear ratios. And of course, I always times my speed gear ratio by the final drive to get my overall output shaft, or I should say drive shaft, CV shaft ratio. And there you have it. There is how a manual transaxle operates. Speed gears, the final drive and overall ratios, and their purpose and design.